So I'm excited to present our work on distributed training of foundation models for ophthalmic diagnosis. This research is supervised by Professor Minhaj Nualam at University of North Carolina at Charlotte, UNCC. In this presentation, I will walk you through how federated learning can be used to develop robust and scalable AI models for ophthalmic disease diagnosis while ensuring data privacy and generalizability across diverse institutions. So let's dive in. Here's the roadmap for my presentation. We'll start with an introduction, then covering motivation and background of this research. We'll discuss the challenges in ophthalmic AI, introduce our proposed framework that integrates self-supervised learning, domain adaptation, and federated learning. After that, we'll go over our data set, experiment setup, and the performance of our models before concluding with key takeaways. I hope by end of this talk, we'll understand how federated learning can significantly improve real-world AI application, especially in ophthalmology. Well, this work is conducted at Quantitative Imaging and AI Lab at UNCC. Our lab focuses on integrating AI into medical imaging, aiming to enhance disease detection and classification using deep learning techniques. To give you a little bit of background, vision impairment is a major global health issue affecting 2.2 billion people worldwide. And what's more concerning is that nearly 1 billion cases could have been prevented with early diagnosis and treatment. Among these leading causes of vision impairment are diabetic retinopathy, age-related macular degeneration, and glaucoma. And we can see some of the example of patients with these diseases. And these diseases can be detected through imaging techniques like optical coherence tomography, or OCT for short. However, early symptoms are often difficult to identify, leading to late stages of diagnosis when treatment are less effective. So how can AI help? Let's take a look. Well, to understand how AI can improve diagnosis, let's first look at retinal imaging. There are different imaging modalities used for ophthalmic disease detection, and two most common ones are fundoscopy, which provides a 2D images of the retina, and then there is OCT, which captures high resolution cross-sectional images of the retina, enabling detailed structure analysis. And probably you have experience sitting behind of this desk to check your retina. And OCT is especially powerful because it allows clinicians to detect subtle changes in retinal layers, making it ideal for diagnosing disease like diabetic retinopathy, DR, and age-related macular degeneration, or AMD. These are some of the samples that we've taken in our lab, comprised of OCT that captures the structure, and also OCTA, OCT angiography that visualizes vascular flow, helping detect early signs of retinal disease by highlighting blood vessels abnormalities. So these images on the right side are, are OCTA. Well, while AI holds promise for ophthalmic diagnosis, several key challenges must be addressed here. The first one is annotation bottleneck. Labeling medical images requires clinicians, and making annotation very difficult and expensive. Also, different hospitals use different imaging devices and protocols, leading to inconsistencies in data that could lead to domain shift when we train AI models. And of course, sharing patient data across institutions is restricted due to privacy regulations. And finally, many clinical sites lack access to powerful GPU clusters that are required for training large AI models. And these challenges make it difficult to develop scalable and powerful AI model. And to overcome this challenge, we leverage self-supervised learning, SSL, domain adaptation, and federated learning. So let's explore these approaches. The first one is self-supervised learning. Instead of relying on labeled data, self-supervised learning allows AI models to learn from unlabeled images by recognizing patterns and structures. This is especially useful in medical imaging where annotations are scarce. In this study, we use mask image modeling, a technique where the model learns to predict mask patches in an image. This helps the model understand the underlying structure of OCT scans without needing manual labels. And here we see an example of model predicting the mask patches. So SSL helps create more robust and generalizable model. The second technique that we've used was domain adaptation. A major issue in AI model is the domain shift, as I mentioned, and that is caused by imaging protocols, demographics, and devices. This means a model trained on one data set might fail on another. So to solve this, we use this domain adaptation technique, or SVDNA algorithm, that transform images from different sources to the target image, making them more consistent across institutions. As you can see in the images on top, or source images. After applying domain adaptation, the pixel intensity and texture of different scans become more uniform, allowing the AI model to perform better across datasets. And the idea behind this is using singular value decomposition of the target. So when we come to the federated learning. It's a game changer for AI in healthcare because instead of sharing patients' data, hospitals train model locally and only sends model updates to a central server. And this method ensures data privacy, that is a major concern in this domain, while allowing collaboration across institutions. It also enhances model generalization by learning from multi-institutional data. And Flower, as a well-known framework for federated learning, is very efficient in managing communication between multiple training nodes and aggregates updates using customizable strategy. And the benefit of using federated learning is that it allows to optimize the resources that are required for training a robust AI model. So it allows to developing real-world applications that are scalable. As we know, federated learning is gaining traction in the field of ophthalmology as several research groups are exploring its potentials. Here, I'd like to highlight some key contributions in the domain. The FedEye platform demonstrates a scalable and flexible end-to-end federated learning solutions for ophthalmology, emphasizing its applicability across various institutions. Another study, researchers focuses on microvasculature segmentation and diabetic retinopathy classification using OCTA data, showcasing, again, federated learning strengths in tackling the specialized imaging tasks. Another study, multi-center collaboration in ophthalmology, highlights how federated learning can be used to enhance diagnosis and disease epidemiology by pulling expertise and data from diverse institutions. And finally, a review of federated learning for ocular imaging provides insights into the progress and future potentials in improving diagnosis workflow. Of course, our lab is one of the leading groups contributing to this space with a focus on federated learning application using OCT data. By building on this growing body of work, we aim to push the boundaries of what federated learning can achieve in ophthalmic diagnosis. Now, let's dive into the detail of our work, see how we contribute to this exciting field. So our goal was to develop a foundation model that can learn robust OCT representation using SSL, handle domain shift with domain adaptation, and train collaboratively across hospitals using federated. Of course, the model should be able to classify multiple ophthalmic disease classification with high accuracy. And we would like to ensure scalable, privacy-preserving AI for ophthalmology. So let's break down the stack, our framework. The first one was mainly we had 4 phases. The first one was local learning, where we train a model on a single data set. This approach, of course, lacks generalization because when it was tested on external data, the model performed poor. Then in the second approach, we conduct a centralized learning, where we combine all the data into one machine, apply self-supervised learning with mask image modeling for pre-training on all the data, and then fine-tuning over each data set. It has good performance, but there was a privacy concern. The third one was federated learning. We pre-train a global model across different data sets without sharing data using MIM and federated learning. And then each node fine-tune the model, the federated learning model, over its own data. And eventually, the most advanced method that we use, we integrated the domain adaptation into the previous phase to improve generalization. So for local learning and for fine-tuning, we followed the conventional deep learning pipeline, consists of image transformation, an encoder, a classification head for predicting the input level. And for self-supervised learning, we have implemented mask image modeling with 50% masking rate in the center of image, ignoring the top 20% and 20% bottom, as they are usually black pixels in OCT images. For the federated learning, we use Flower to orchestrate the process. Each node pre-trains locally and sends the model updates to the central server that resides at UNCC, and then the server aggregates these updates using Fed average. We pre-train models for 1 to 5 rounds and compare the performance. Then for the domain adaptation, we put a target image inside the server. The server aggregates the eigenvalues and eigenvectors of that image and sends it to each federated learning nodes via fitconfig method. Then each node ran on fly the domain adaptation transformation to apply this transformation on their own data. For our purpose, we use 7 OCT data sets, including 6 public and 1 private clinical data from UIC. And for federated learning, so we simulated 7 nodes. Here we can see different percentage of data allocated to each phase for training, validation, and testing. Consider that the DS7, the major part of that was considered only for evaluation. Each data set has its own unique set of labels. So we considered a multi-class classification problem for each of them. We have 7 different problems. There are also common labels between these data sets. So we use that common labels for external testing. The model that has been trained on DS1, then tested on other data sets. And again, to clarify, for each phase, for example, for local, centralized, federated learning, and domain adaptive federated learning, we trained 7 different models and then evaluated them on internal and external test sets, except for DS7, which was a unique external data sets coming from UIC. And we tested different hyperparameters, image resolution, and optimizer to come up with the best numbers. And for federated learning, once again, we have 7 nodes, 6 of them with the server at UNCC, sorry, and 1 of them at UIC. So to compare the performance of our model, we use macro AUC-ROC for multi-class classification problem. As you can see, the SSL-based model outperformed local models by 10 to 40% across different data sets. And FDL5, that is federated learning, that means federated learning model trained for 5 rounds. And that FDL is domain adaptive federated learning. They are also achieve good performance. When we tested on external data sets, we can see that the DAD FDL5 achieved the highest generalization performance, that demonstrating the value of federated learning and domain adaptation. And when we check the performance on DS7, we can see as we plotted the AUC-ROC for different approach, local, central, domain adaptive federated learning, you can see again that FDL5 achieved the highest performance. So in conclusion, we implemented a framework that has privacy preserving, no raw data ever leaves the node. Federated learning ensures that patients' privacy is fully maintained, addressing concerns around data sharing regulation. This approach was scalable because we can easily accommodate a new node without requiring them to share data. It reduced the need for annotation. By leveraging SSL, we can minimize the number of labeled data. And of course, this framework is robust because it can learn from diverse imaging conditions and devices. These benefits makes this our framework highly for real-world medical AI applications, especially in ophthalmology. And thank you all for your attention. And if you have any questions, I'm here to answer. And I would like to thank our collaborator.
Great. This was a fantastic talk, Sina. Thank you very much for providing all the details. And I think also it was amazing to see that there are some live captions for your talk. That was I've never seen it before, so that was great to see for the first time. I have one question, in particular, when you were talking about domain adaptation, you were saying some of the sources of these domain adaptation issues would be maybe different sites, different hospitals using different protocols, maybe different devices, populations might be different in different hospitals because of how demographics are distributed. Yes. Were you able to identify which of these is the most problematic one? Or do you have some theories of which one is the most problematic in your particular study?
In this study, we found out the device itself makes the most contribution to this domain shift. As you can see, these are different images, random images taken from different data sets. These are like 7 images coming from these 7 data sets, and each of them has taken using different device. And you can see they have different image intensity. So we randomly pick some subject, one subject, and we put it here, and you can see the device that they used is basically affects the most on the image intensity. And there are like different devices on market, the different OCT devices on market.
Okay, interesting. So I know that your method was built to overcome these shifts, domain shifts, but even before, for example, instead of leaving all that task, potentially very difficult task to the model and the learning stage, did you consider doing some data homogenization to homogenize all the or pre-process all the data sets in a similar way each side? Or do you think some of these, I think these things are not easy, especially in FL when you don't have access to the different sites, right? But I think there are some level of pre-processing that could be executed in every site. Do you have some thoughts about that?
I would say in federated learning, especially in this medical domain where you have restricted access to their data, you probably rather sending all this configuration from the server to each node. So in our implementation, we put the same image transformation for SSL, and for fine tuning, again, same image transformation. For example, all the images would be resized, all of them would be normalized. But also apart that, we've seen adding this domain adaptation can improve the performance of our model. So we said, okay, apart from this, we can also apply domain adaptation, and the configuration once again can be sent from the server to each of these nodes.
Okay, yeah.
Hi, Javier. I just had a quick comment on that. By the way, really nice talks, and thanks everyone. One of the things that we wanted to do is like one of the beauty of federated learning is we are able to use data from different sources. So ideally, we would want some difference in them because they're coming from different demographic profiles, right? So the scope of domain adaptation is not just homogenize them, is just keep their uniqueness, is just if there is if we can improve the intensity, brightness, like those more high level things to make our model more optimized. That's what our goal is. We don't want to effectively change them too much. So there's like a sweet spot where you want them to be different enough, but then so you just don't want to mess with the model convergence. So this is the domination basically helps with that, and that's the goal, I guess. And we also do it randomly so that not say, let's say we do it for dataset 1 as the target image, then we switch it up so that every time it's a little bit different so that the model are not biased. Otherwise, we saw that the model can be biased towards the dataset that has the highest amount of data. We also don't want that because ideally when we scale this up, we'd have like say 100 institutions, right? And we want the smaller institutions to be taken seriously as well, not just say one institution is like 1 million image data points. So yeah, so we're still working on this, and like this is still an interesting research topic.
Yeah. No, thank you for jumping in with a clarification about, it's not right to try to erase the particularities of each site. I 100% agree. So I think your comment was on point.
Yeah.
Thanks for that. So I don't know if there are other questions, maybe from the audience. I will check on Slack briefly. If there is anyone with a question, please jump in. If not, I have one extra question. Oh, yeah.
I'll just go. In terms of next steps, I mean, I really like the presentation. Is it to go to add more, organizations to your federated setup, or what's the plan from your side?
Of course, yeah, we would like to include more data from other institutions, from other demographics to our framework, and of course, exploring other federated learning strategies. For example, in this study, we only go for Fed average, but we know that there are many other strategies for averaging that we can also apply here, and we can improve the performance of our global model.
Do you see a need for personalization when it comes to this?
I don't think so, because we pre-train, we are in the pre-training phase was conducted using federated, and then each of them was fine-tuned on its own local data. So the personalization was somehow conducted, somehow integrated inside this framework. We can, of course, there are other ideas that what if we somehow reduce the number of remove the fine-tuning phase and go from training to inference instead of having pre-training, fine-tuning, and inference. There are some ideas here that we would like to also explore them. But at this time and at this with this framework, there is no need for that.
Great. Yeah, I think that was a bit the angle that William was asking about personalization, whether like the global model you are then doing a fine-tuning in each different site, because in the end each hospital might have its own demographics, like maybe it's a children's only hospital, these kind of things. Pretty interesting. Yeah, I think I was going to ask also about personalization, but I think we have already ticked that box. So I will ask very briefly, and my final question is about what, among all the possible, let's say, dimensions for heterogeneity in each site, we are talking about the domain adaptation related heterogeneity, but there is also like the quantity level heterogeneity, like some sites having much more data than others, because at the end of the day, some hospitals are much bigger than smaller clinics and they have more data. Did you have a chance to explore this aspect as well?
I mean, in domain adaptation, yeah, here there's the slide. Of course, there's the amount of target image intensity that you would like to consider for your source image. You can consider there's like a threshold on how many eigenvalues you want to take from the target image. Because if we go through the algorithm says we remove the least important diagonal values of SVD from this source image and replace it with the target image. That is basically the noise information of the target image. But you can change this threshold to see how much do you like your images to adapt to the target image. And as Dr. Allen mentioned, we do not want to convert them completely to the target image, because that might in this case we might lose some information from these differences. And of course some devices, OCT devices, are very similar. For example, these 2D images, as you can see in a source image, the first two on the left side. I'm not sure if you can see my pointer.
We can see it, yes, we can.
These two are very similar because they kind of use the same device. And then the third image and last image, they also have similar intensity because, again, they kind of use the same device. This is also something that we were able to explore, that's seeing what kind of device they have used during the image capture.
Cool. Really, really interesting work. So thank you very much, Sina, for all the details. And if anyone in the audience is still interested in reaching out to Sina, well, Flower Slack is a great place to start those interactions and maybe even collaborations.